Part 3 of Chapter 21. Circuit containing capacitors. So capacitors can also be connected in series or in parallel. For example, here we have 3 capacitors connected in a parallel fashion. When capacitors are connected in parallel fashion, the potential difference across each one is the same. So the potential difference across C1 is the same potential across C2 and the same potential across C3. So in other words, I can consider one capacitor in position of these 3, and I call it CF equivalent or CF total. Okay? So capacitors in series would be the same. Capacitors connected in series do not have the same potential across, okay, but they do all carry the same charge. So in other words, Q1 and Q2 and Q3 will be the same. Okay, Q1 should be equal to Q2, should be equal to Q3, and should be equal to Q, which is the amount of charge in the equivalent capacitor, or Q total. Okay. The total potential difference is the sum of the potential differences across each one of them. In other words, if you want to find a V total or V of the battery, you should find V1 and then V2 and then V3 and add them up. If you have more than one, then and more than 3, then you add whatever that exists. So kind of like that. So let's talk about capacitors in series and in parallel. Capacitance is proportional to charge. We know that Q is equal to CV. So we know that Q, or the charge, is C times V. While resistance is inversely proportional to current. So I is VR, we know from Ohm's law. The equivalent capacitance or capacitor in series and parallel has the opposite from that in the resistors. So in a parallel, you add them up, and capacitors in the series, you have the same thing. So C of total when they are in parallel is C1 plus C2 plus C3 and so on and so forth. But when they are in series fashion, C1 over C total is 1 over C1 plus 1 over C2 plus 1 over C3 and so on and so forth. Okay. Regardless of how capacitors are connected, they always have equal amount of charge on each plate. So one plate of the one capacitor is positive Q, the other plate of the same capacitor will be negative Q. One capacitor, by the way. Okay. So let's take a look at this. What is the equivalent capacitance of the combination rule? And by the way, one more thing, if I would like to point out something very important, is that when you have a capacitors in series, okay, they do not have the same potential difference, but they all carry the same charge. Okay, so this is very important. So if they are in series, okay, if they are in series, that's the way that you find the total capacitance. And once they are in series, then your Q total would be Q1, would be Q2, and so on. So let's go back to this. So what's the equivalent capacitance? C equivalent of the combination below. So we have 2 capacitors that are connected in series, okay? So C of total, 1 over C of total, is 1 over C plus 1 over C. In other words, C of total is C squared over 2C, which is C over 2. So here I can replace these 2 with a capacitor of C over 2. And then that would be in parallel with C. So then I have a parallel fashion between this new capacitor, which is C over 2, and my old capacitor C. And then I just have to add them up. So C total, because they are in parallel, C plus C over 2, which is 3C over 2. So RC circuits. In a circuit containing only batteries and capacitors, charge appears almost instantaneous on the capacitor. So if there is no resistor, in other words. However, if the circuit contains resistors as well, this is not the case. So if this switch is on, if I connect this switch like that, there will be an I, or a current, going through the resistor and a capacitor. But this current will not instantly, because of the existence of resistor in our case, this charge will not instantly be available in our plate of the capacitors, okay, because of the existence of a resistor in the circuit. Now, RC circuits, mathematical relationship. So when a capacitor is connected in a circuit with a resistor, it takes time. It takes some amount of time for the capacitor plates to charge, okay? That time is called tau, which is R times C. So this is very, very, very important. So this tau is R times C. The resistance, the value for that R in ohms, times the capacitance of the capacitor. Okay. The charge in the capacitor are at any given time that the capacitor is charging is equal to this relationship. So at any time, Q equals Q0 times 1 minus e negative t over tau. Okay, and so this tau is RC, as you can see here. If t goes to 0, let's consider two cases. T equals 0 at the beginning. Okay, so e to the power of 0, a number to the power of 0 is 1. 1 minus 1 is 0, so Q would be 0. If t goes to infinity, means it will take a very, very long time, then this would be a 0, and then Q would be Q0, if that's the case. Once the capacitor is charged and power source is removed, let's say that we remove the battery, the capacitor will discharge. And so it will be like a battery itself. The charge at any time is giving, in this scenario, is giving to through this relation. Okay. And if you want to study that equation, what we have is that Q is Q0 e to the negative t over tau. Let's consider two cases. At the beginning, if t is 0, e to the power of 0 is 1. Okay, then Q is Q0. We have removed the battery, okay? Now our capacitor is full at time equals 0. Our capacitor is full, okay? At t goes to infinity, if this goes to infinity, then this would be 0, then your Q would be 0, okay? Because then your capacitor, once you remove the battery, your capacitor looks like as if it is a tiny short-term battery for the circuit. So, charge for a charging RC circuit. Here is a charge versus time for the RC circuit. This is essentially what we have here, right here, okay? Right there, okay? So at the beginning, there is no charge in the capacitor. And then as time goes by, 1 tau, tau is RC, by the way, okay, R times C. As time goes by, you have your slowly and slowly and slowly in an exponential fashion, your circuit or the capacitor will get charged, okay? And you can also compare the current. You have a high current at the beginning because your capacitor is not full, so it lets everything to go in. But as the capacitor is getting full, okay, the current will drop. So one more time, this is the charge. At the beginning, there is no charge in the capacitor. And as time goes by, the capacitor is getting fuller, 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 and fuller. As it is getting fuller, your current is dropping, okay? So this is the current, because once the capacitor is getting full, it does not let the charge to go through, okay? It doesn't let charges to go through. And so you have less current as you move along with time. Now, there are different examples or the usage for these capacitors. For example, heart pacemaker. The capacitor is used to determine the amount of time between pulse from the pacemaker. The capacitor is allowed to discharge, okay? And when it reaches a particular level, the voltage pulse is delivered, then the capacitor then gets recharged. And again, there are a lot of examples of the use of a capacitor. Almost everything that we use in a daily life, there is existence of capacitors inside. So there will be millions of examples if I can list them here. And let's talk about the circuit breakers and fuses. So the circuit that has more than a safe amount of current is said to be overloaded, okay? If this is dangerous. Connect fuse in series along the main supply line will help us to, prevent that overload to happen. The fuse is rated with how current, it will allow to go through. So depending on what type of fuse you want to use, when the amount of current exceeds the rated amount, then the fuse will blow out or melt, and then you have no current then. Fuse have, for the most part, recently actually replaced with circuit breakers, which use magnetic strips to open the switch. There is a certain level, safe level of amount of current inside the circuit in our houses, and if it goes past that, we have the fuses or circuit breakers that they can break the current and does not prevent a harm to happen either to the circuits or prevent from fire or things like that. So this is the last section of this chapter. A common misconception is that the voltage kills you. This is not. It is not actually the voltage, it is the current. So V doesn't do anything if you get an electric shock, okay? So V doesn't do anything. It's the I which is responsible. So V is not killing you, it's I, it's the current. This can occur if 100 milliamp or 0.1 amp flows through the body. A 60-watt light bulb, okay, this is a power of that. It is turning 60 joules of energy to heat and light per second. Draw a 0.5 amp in a normal operation, okay? Draw a 0.5 amp in a normal operation. The amount of current going through the body is inversely proportional to the body resistance, right? So we know that I is V over R. So in other words, I is proportional to 1 over R. And what it means is that if our skin is dry and the body's resistance is about 500,000 ohms, which is a huge number. So this number R is huge. That means your I is low, okay? And from a current of 110 volts, the source would be probably somewhere around, if your skin is dry, 0.22 milliamp, okay? But if our skin is wet, let's say that you're right out of shower, and the body's resistance is greatly reduced because you have water, which is a perfect conductor on your skin. So then what's happening is that you have reduced your R, and then I will increase. Okay, so that means in this case, the current from 110 volt power source would be 1.1 amp, which is huge to kill you. This is why we say appliance should not be used near the bathtub. In addition, how the current flows has an effect. If current flows into your hand and out of your elbow, it won't necessarily kill you, it will still hurt you. But if the current flows into one hand and gets out of your, for example, legs or the other hand, it will likely kill you because your current is going through your heart. So it's also important which direction the current is going to. So very quick summary of chapter 21. Electric current is the flow of electric charge. The unit is ampere. 1 amp is 1 coulomb per second. A battery uses chemical reactions to maintain a potential difference between its terminals. Okay, that's why you always have a certain potential difference between positive and negative. And the potential difference between batteries' terminals is, in ideal condition, is the EMF, electromotive force. Okay, work done by the battery moving charge around the circuit is W is delta Q times the EMF that's right here. Okay, so that's the work that it's doing. Direction of the current in the direction is the direction positive charge would move. We actually know that the positive does not move, but this is the conventional type of current that we think. Ohm's law is stating V equals IR, or the voltage across of a resistor or a device equals to its resistance times the current that's going through it. And the relationship for a wire, for the resistance inside a wire, is R equals rho, which is the resistivity, depending on the wire material. If it's gold, if it's copper, you will have a different rho, times the length of the wire over A, which is the cross-section area. The resistance of the superconductor drops suddenly to 0 at the critical temperature. And we talked about the power in the electric circuit, which is P is V times I. And depending on what we want to say or what we want to use, we can talk about the power loss, which is P equals RI squared, or power provided, which is V squared over R. And they are the same, by the way, but depending on what we talked about, we use a different form of equations. Energy is equivalent to kilowatt hour. In other words, 1 kilowatt hour is 3.6 times 10 to the 6. If you don't remember, go back to previous part of the video, and I talked about how this is 1 kilowatt hour is 3.6 times to the 10 to the power of 6, and the electric company is charging you because of the energy that you're using in joules. And then what we talked about, the resistance, the resistance for for the resistance in series, the R equivalent or R total is that you add them up. Okay, but for the resistance in parallel fashion, there is a relationship. 1 over R equal is 1 over R1 plus 1 over R2 plus 1 over R3 and so on. If you have two resistors, if there are two resistors, so let me actually write it here. If there are two resistors, okay, then R equivalent or R total is R1, R2, R1 plus R2. Okay. Junction rules in it was one of the Kirchhoff's laws that all current that enters a junction must also leave it. And loop rule was that the algebraic sum of all potential charges around a closed loop must be 0. And we show that this is in fact sigma V should be equals to 0. We have capacitors in our circuit, and if they are in a parallel fashion, you can just add them up, C1 plus C2 plus C3 and so on, and they will have the same amount of charge. So in this case, Q total should be Q1 plus Q2 plus they should be all the same. So let me go ahead and replace these with a equal sign, okay? Q3 and Q4 and so on. And inversely to resistors, if they are connected in series, then you would have 1 over C equivalent of equals to 1 over C1 plus 1 over C2 plus 1 over C3 and so on. And then if you have two capacitors, then C total is C1, C2, C1 plus C2. For charging capacitor in an RC circuit, tau in our case is R times C. R is the resistance of the resistor. C is the capacitor, it's the capacitance of the capacitor. The Q or the charge have this type of relationship, and this is, by the way, Q0. Okay, this is Q0. We talked about it. What would happen if T goes to 0, and what would happen if T goes to infinity? We talked about it. And the I, or the charge, or the current would have this type of relationship. And this is, by the way, I0. Okay, this is I0. And we talked about it. What would happen if T goes to 0? And what would happen if T goes to infinity? Once you remove the source, once you remove the power source, okay? Once you do that, then your capacitor is acting like a battery or a small or a temporary source, okay? Creating this amount of current. And in fact, this is for that. So this is for when we are discharging a capacitor. Once the power source is removed, then your Q is in this fashion. So one more word for the I. Once you connect your battery to a circuit, to an RC circuit, okay, to an RC. Once you connect your battery to a RC circuit, at the beginning you have a huge amount of current going through, but as the capacitor is getting full, the current will drop and it will get to 0 once it's completely full. It does not let, your capacitor does not let any charge to go through, okay? And at the beginning, you have almost no charge in your capacitor, but as the time goes by, you will have a fully charged capacitor, okay? So we have amp meters and voltmeters and multimeters. Multimeters can be either amp meters and voltmeter, depending on the setting that you want to use. Measure the current. It is connected in a series way, okay? Resistance should be as small as possible. And for voltmeters, measure the voltage, and it should be connected in a parallel fashion, in a parallel way. So if I have a resistor, for example, R, and amp meter should be connected here, okay, to measure the current that's going, and voltmeters, V, should be connected here to measure the voltage across this R. Is connected in parallel fashion. Resistance should be as large as possible for the voltmeters. And multimeters are amp meters and voltmeters combined. Okay, this is the end of chapter 21. Let me know if you have any questions. You can comment or you can email me. I'll be happy to answer those.